Good morning, everyone, again. So if you just joined us in the past couple of seconds or minutes, good morning. So today we are going to do some extra stuff, which is going to be a bit confusing. To be honest, when I was doing it last night, reviewing it last night, I realized that it is still confusing for me. So it might be confusing for you also. So for today, I'm strongly suggesting you that you should follow every step one by one while I'm doing it. If you try to just watch, you're probably going to have some issues later on when you're trying to replicate whatever I've done. So please go ahead step by step and follow me. If you have any question at any moment, ask. I will wait for you to catch up with the speed and continue with us for the rest of the session. Is that okay with everyone?
Yes.
Good. So
yes. And by the way, Adrian, where is the files needed today?
for the part that we want to work today, it's in okay. Okay. So if you go to HAL files, let me just bring the student view, so you'll see the exact same as what I see. Okay. So student view, which is something you should see here, and then you go to HAL and class files and HAL04. So here there are two files. Open the Rhino file and open the Grasshopper file. I think if you open the Grasshopper file, it's going to help you to figure out what we are trying to achieve. And then we can actually start working from scratch. Again, it's a little bit challenging, the thing we are going to go today, because the Grasshopper part is a bit challenging. If you have like enough experience with data structure in Grasshopper, it's going to be way easier for you. So please go ahead, open this Grasshopper file and also this Rhino file. But we will eventually get back and work with the a blank Grasshopper file to review everything from the past session and also do the new parts. Okay, so if you open that file, you will see there is something like this in the air, floating around. And the Rhino file is basically the file that we used from the last session, but it has some extra elements inside of it. So basically this drawing of these curves is actually added. So if I activate this, is it here? Yes. Okay, so basically this is a piece of curve that you can see actually on the surface, like it's a flat drawing, which I used actually the magnetic field or force field in Grasshopper to generate, and then I used this plane to project it onto this sphere, and the result is actually this. So it's just like kind of nice, complex drawing that I just generated here as the beginning point. We can also start with something, actually we will start from something way less problematic. So just open the Rhino file, and I'm going to create a new Grasshopper file. And as always, just to recap everything, please spend the next 5 or 6 minutes to generate the new robot, a HAL procedure for the robot to generate the robot. Start with the really simple toolpath, and then the IKSolver and the other stuff. So just a couple of minutes we are spending to draw this one in order to, again, warm up with the process. So while I'm doing this, you should also doing it on your computer. I'm just doing it as a source of like, refreshing the class material. Okay, so if everybody is ready, let's start it. We're going to quickly make the setup here. So as always, first we need to have our robot. So I'm going to use the robot preset and then double click on it because it's 120. I'm going to make a speed preset. I will call it like drawing speed. And I will set the velocity at 100, which is a good number for this robot. And I will go for a zone value, and I call this one accurate. And the TCP zone is going to be set to 0. And I'm going to use the tool 0 because you don't need to define that tool specifically. Okay. These are the setup: speed, robot, zone value. No problem. I'm going to keep the toolpath here and toolpath creator. Where's that? Okay, here. And I'm going to make one blank target here for now, like an XY plane that connects to this simple point here, and set one point. Good. And I would say, okay, this is my target, and it uses this speed value, it uses this zone value, and it uses this tool. So far, so good. I want to make the IKSolver, so I'm going to make it another group. I want to have the IKSolver. And as always, it needs to read the data from the robot. If this line here is actually a little bit confusing for you and it makes you think that, oh, this curve is actually connected to this, you can right click on the target and make it to look like a hidden line. You see that? It's still connected from the robot to this IKSolver, but when you unclick it, it doesn't show up. So you have a cleaner setup here and everything seems a little bit better. So let's keep it here. And I want to connect the toolpath, but I know that I need to use that mode switch. And I know that for that one, I need to have this mode selection. So I want to have this toolpath preview. I want to have, oh, not this slider. This slider is the one I'm looking for. And this is the toolpath. And the toolpath here is going to be my friend. And also, I want to see the geometry. So I will have a toggle to say that, yes, I want to see the geometry. Okay, so we are done with this part. I think now it's a good time to do the post processor. Oops. And get this and the toolpath from here. Okay. And then I can go for quick task, which basically converts this one into a piece of code. To keep everything clean, I will go for merge. And these are the declarations. Targets are here, and operations are motions. I can check and see if everything is working. Let's check that. Yep, I have almost everything that I want. Good. So far, so good. We are having all the usual suspects and no problem with anything. And as always, I forgot to increase the size of my UI. So I'll do it right now. 200% is a better choice, and my eyes are hurting. Okay, so let's go for Rhino and see what. Okay, good. So everybody's on board?
What's after the IKSolver?
Okay, so IKSolver was here. So what was your question? Is that clear?
Oh, sorry, I was muted. Yeah, I was just wanna look at what's after the IKSolver.
Yeah, it's a post processor, which is the one that converts the data from the IKSolver into motions and other commands. And then we need to use the quick task. And here, somewhere at the middle, is our battleground today here.
Just to clarify, are we not passing in any information when we merge at D3 and D4?
Right now, there is nothing here because it's using the tool 0. It automatically eliminates the definition for tool 0 because tool 0 is already embedded in our rapid code. If we try to manually define tool 0, rapid is going to get really angry and it's going to throw an error to us. So post-processor automatically ignores that tool 0 and doesn't send anything here. And then we didn't identify any work object also. So that's why these two are orange. Is that clear?
Well, like I have a question. Like at the first beginning, like when we said the target, the point is from the Rhino file, or
yeah, it can be from anywhere. Right now, just for test, I introduced it from Rhino because I wanted to give us some like flexibility. Okay, so let's see what's going on. So to be honest, this is the story for today. We want to, oh my God, I should never trust Zoom and its interface. So basically what we are going to do, let me just bring up the other file that we had. Okay, what we are going to do for today is to actually grab this really complex geometry and try to figure out if we can actually run this one with an RGB LED. So we want to make some light painting with this model here, but we want to do this light painting with like RGB lights. So as you can see here, the targets at the bottom are green and the ones at the top are blue. So somehow we want to get this data and make this, light painting something cool, or maybe any different color that we want. So we want to somehow not only control the robot to go into a specific direction and location in its path, but also it needs to get different colors while doing this. And I will explain like different steps of this one, like the hardware that we set up for this one, the software that should go on and everything. But it is a little bit challenging. So for today, we are going to focus on the Grasshopper side. Okay, so I'm not going to start with such a complex geometry. I'm going to start with a really, really simple geometry, which makes it way easier to work with. So I'm getting back to my file, and I need to actually save this file because I don't want to lose it. So I'll say in last progress. Okay, so right now we have the robot, and we want to go for something really, really simple. We don't need this part, so let's hide it. We don't need those things at the back. Let's hide them also. Okay, so let's see. I want to just draw a line, maybe a spiral or something like that, and to try to see if we can do that, light painting with different colors on it. So to do so, I'm going to make, let's see if there's an helix option here. We don't have helix in the Grasshopper, I guess. So let's do that in Rhino. So in Rhino, you have this option to draw a helix. So basically, you select a point. I selected the point that I just selected, and you can actually make a helix like this. My suggestion is actually to draw 2 points. So I'm going to copy that point, make a vertical copy of that one. So I'll have 2 points, one exactly above the other one. Now I can use that helix command. I'll select the first one, I'll select the second one, and then I can actually set the radius for something like this. So I will get something like this. It's a helix, it's a spiral that moves up. So you should have something like this. So the command is called helix. And you can actually by default select a vertical one, select 1 point, then select another point. And you can say that like maybe it can have like 3 turns, and you can set the diameter for something like 12. Maybe that's a better one. And you get one. Oh, let's see. Okay, good. The other one was like too complex. Okay, so we have a helix here, or any other curve that goes up is fine for this workflow. So we have this one. I'm going to introduce it into Grasshopper and do the usual process. We select the curve, and yeah, it's it. That's it. Have you selected that one? Select one curve. Yeah, it's already selected. And I'm going to hide it because we don't want to get confused with everything. And we need to divide this curve into a lot of targets. So I'm going to divide it. And as you know, Grasshopper has different methods of dividing a curve. And this means that we can divide a curve by a fixed number of targets. For example, I can say that please divide this curve into 10 sections, and it's going to give me 11 targets. I can say that please divide this curve in a specific distances along the curve. And I also can divide a curve in special distances from each other. So I think for now we can go for divide by length, which guarantees that the targets are equally spaced alongside the curve. And it's slightly different from the divide distance. So I'm going to say that like every 5 millimeters, give me one target. So we have these targets are each like 5 millimeters away from each other. If your computer cannot handle it, you can make it 10, 15, or whatever. It doesn't make that much of a difference as long as you have more than a couple of targets. So as you can see, it starts from the beginning of the curve, measures 10 millimeters on the curve, put a target there, another 10 millimeter puts another target, and it goes all the way until there's not enough space at the end of the line to make another 10 millimeter distance, and it stops. As you can see, it basically doesn't give you a target at the end necessarily. But if you use divide curve and ask it to give you a specific number of targets, you can see that it always gives you the first and the last. For this work, it doesn't matter if it doesn't give us the last point of the curve. So I'm fine with these targets. Okay, let's have a look and see how many targets do we have. So it says that we have these points. And if you scroll down, we realize that there are 40 targets. And yes, it's 39 plus 0. So it's plus the first one, which is the item 0, it's 40. So it's good for us. So if you are familiar with Python, this is the exact thing that happens in Python, starting from 0. Okay, so we can introduce these points as our targets. No problem. The robot says, piece of cake, and it can move along them with no problem. Okay. We have absolutely no problem with this one. Is everybody on the same boat? You all have it?
Oh,
go ahead.
What extra? Okay, no, yeah, you're just moving the points along the XY. Okay, I just want to see.
Yeah. That's the method that we are defining our basic targets, because every target should have not only a location, but also an orientation. And our go-to orientation is using XY plane for now. Later on, we are going to do way more complex solutions for this. Okay, so we have these targets. I'm going to move this robot somewhere at the middle, but this is just a definition of our toolpath. We still need to find a way to somehow assign colors to these targets that we have here. Okay, so a bunch of targets, a bunch of places that the robot should go, but we still need to make sure that we can assign somehow different colors to this workflow. Okay, let me bring my iPad so I can actually draw something for you on the table. Give me a second. Okay, great. So I'm back with my iPad so I can draw something on this for you. Okay, so let's see what we are going to do. So basically here, we want to do one simple thing. We want to say that, for example, so that we have all these targets from down here all the way to up here. And we want to find a method to apply color based on height of each point. So I want to say that if the point here is red and this one is green, everything in between should go along a spectrum of red to green. Somehow I should break down this problem into assigning the color and the z value of each point together. Okay, so I will do this. I'll try to read the z value for each target, and then somehow I try to use a component in Grasshopper that assigns a spectrum of colors, a gradient of colors into these points. Okay, so let's do that part. Let's see how we can actually read the z value of a point. So if you double click here and type XYZ, you see that we have one option that says deconstruct a point. And it basically reads a point and then gives you X, Y, and Z of those points. So I'm going to use this component and I can use it here. Let's do it here. Okay. So these two components are actually holding the same thing. So that's not a problem. So if I have a look at the Z values, I will see that these values are coming from a wide range of numbers from 99 all the way to 172. So we have numbers from 99 here to 172 here. And somehow I want to use them to generate colors. Okay, the component that takes care of these colors for us is called gradient, and it's here. So if you double click and say gradient, it shows up here. And here's the catch. This component receives a first number, a second number, and a t value. What are these three? So basically, it says that if you give me a number and say this is the code number for a color, I will try to find it on this spectrum if and only if I set this part as L0 and this part as L1. What does it mean? It basically means that it's going to collect three numbers. The first number, it is going to be start of this spectrum. So for example, I can say that the beginning of this spectrum is 99. Okay. And then the last point of this spectrum is like 170. And then if I give it a number between 99 and 170, it's going to find which point on this graph is going to be that number. So for example, if I give it 105, it's going to tell me, okay, 105 is here, so the corresponding color is here. If I give it 169, it's going to be here, and it's going to be a dark red. So do you see it? It just tries to make a spectrum between two given number, for example, L0 and L1. And each number that you give it in between these two spectrum, these two limits of the spectrum, it tries to map them to the colors that you may have above it. And in this case, it's starting from this like pinkish thing to this like dark red or scarlet color, whatever it is. We can go for another spectrum that goes from green all the way to yellow and all the way to red. So what I'm going to do here is to actually provide these three numbers for my system. So I need to know what is the lowest number that I have, what is the highest number that I have, and what's the number that I want to assign to something right now. There are different ways of doing it. I'm going to use a component that calls bound. And bound is actually gives us the minimum and maximum of a data set. So I'm just going to use this bound. And if you look carefully, it gives us 99 and 172. And it's basically a range. Range means that it has two numbers combined together and there's a 2 in between. So it's not two numbers that we can actually use. So we need to deconstruct this domain or domain here. And then it gives us the beginning and the end. So you see that the start is 99 The end is 172, so I can use these two. And then I can use the Z value for each one to give me the corresponding color. So let me just keep these things here, keep it nice and clean. Okay. So once I use the Z value to find the highest Z and the lowest Z, and then I use the same Z value to get the number of the color code for each target that I have. And like many other softwares around computer graphics, we are using 3 numbers to define a color. So basically, when we have 3 colors, it's going to tell us what combination of red, green, and blue is this color. So the first one is green, so it means that it's full green, 0 blue, 0 red. And the next one is basically a little bit of red, more of green, no blue. Actually, in this spectrum, we have no blue in any of these colors. And we are just playing with these 2 numbers, R, which means red, G, which is green, and blue, which is 0. And then you can see that this number increases, and then this number actually moves all the way to the top and then goes down. But anyway, if we use these numbers to define the rendering of each point, we will get the same spectrum. So is that clear for everyone what we have done here? No question?
How do you change the gradient?
So you just go here in this corner, right click, and change different presets.
Okay.
Yeah. And then you can actually play with them. Like you can do this, you see that the spectrum is changing.
Why do we still need to connect to Z?
To Z? Oh, let's see. Here, Z in this path is trying to give us some information about the total data that we have. So it tells us what is the maximum number and what is the minimum number. And then we use the same Z in order to define the color for each point. Just think about it this way. We have grades for each student in the class. For example, we have 3 grades, 1A, 1B, and 1C. Then we use this whole grade to see what's the highest grade and lowest grade. So we know that there is an A and there's a C. And then we feed it into this gradient to tell us like for that A and for that B and for that C, what color we should use. So this path is actually just giving the value for each single target. And that's why we have like 40 targets at the end here. Okay, so we have the colors. And now we need to assign these colors to our data, to our points here. So for that one, we use a component that's called custom preview, which receives an object and the material, or in this case, the color of that object. So we want to see these points with the specific color that we generated. So I can just select these points and then apply this color to them. And if you look carefully, you can see that we have these colors applied to our points. Okay, so we have this gradient of colors. Does that make sense? This custom preview component is just basically overrides the colors that Grasshopper shows us, and we can see what's going on in Grasshopper. So it's just basically a material assigner. So I'm just going to make this gradient very simple and subtle, like something like this. And maybe we can actually get rid of some of the in-between points. So I'm just dragging these points down and they are disappearing. And I prefer to go for something like, I double click on that point at the end. And instead of that color, I will go for cyan or something like here. Yeah. Yep. Okay. Seems a little bit better for me. Okay, so we have this one. If there's no question on this side, let's go for the next step. So this is the coloring part, which is really interesting. So let's make this a little bit. First, we need to make this one smaller. And now we can do this. Good for us. Everything seems cool. Okay, now it seems it's fine. We have the colors, everything seems fine, but what was that again?
I have a bit of an issue. So basically, I didn't have the these sort of points little component. I just directly started like from the plane, like the XY plane. I put in all the inputs.
Okay, so you use the XY plane instead of the point?
Yes. And so,
I don't think if it's going to make any problem, but let's see. Let me just do something cool here. So if I double click on this wire, it's going to give me this. And let's see what will happen if I connect everything from this. So basically it gives you the colors for the planes, but you see that it's a little bit hard to read. So you just need to use, for example, the points from here directly. You see that? Or either using this one, it's the same.
Yeah, maybe I still need to, like I did that, but the colors didn't necessarily show through the preview.
So do you have these, like, can you share your screen for a sec so I can see what's going on over there?
Let's see. Let me
just give you the options to do that. Okay, so I should stop sharing myself, and then I need to advance sharing. Go ahead.
All right. So. Oh.
Okay.
I'll just leave it there.
Okay, no problem.
So basically,
first, can you move your robot up? Like, go to the slider that does the simulation, the visualization, and make it 0. Okay, good. And then hide all the points before it. Whatever you have before. Yeah, it's actually, yeah, that divide length, just hide that one.
Let's see.
Hide is the one with the blindfold. Okay, good. And now you have those points at the bottom. So hide that point component also.
Oh, okay. Okay, I see
that. So they're overlapping. So Grasshopper has this problem a lot because basically in Grasshopper, when you're making a new component or you do something, it just duplicates objects on top of each other. And it prevents you from seeing them one after each other. And that's a serious problem. So it's a good idea to actually keep this habit of hiding whatever you're not actively using. So it's not going to interfere with your visual communication. Or you can actually use the options on the top, that barrel that has like half of it green and the other half is actually somehow like faded. That's going to help you to just see what you are selecting. Okay, so I'm going to stop your share screen. Good. Oh, did I open the Photoshop? Yes. Okay, so I'm going to continue sharing my screen. Somehow my computer is not happy with that. Okay. Yeah, I mistakenly tried to run Photoshop. So give me a second until I close Photoshop. Oh, too many robots. Even in my Photoshop. Oh my God. It wasn't supposed to be here. So let's go back to here. Okay, good. So the option that I was talking about is actually this one here. Here. So if you use this option, Grasshopper is only going to show you the objects that you have selected actively, but it doesn't work when you are working with preview, custom preview, because whenever you select something in Grasshopper and you ask it to show it to you, it's going to show it as green, and whenever it's green, you cannot see the real color. So this is the way we should handle it. Okay, this is fine. We have no problem on this side, but let's see how can we apply this color in reality? Because right now we just see it in Grasshopper. It doesn't make any sense. We need to find a way to send this color to some system on the robot to have it available for us to work with. Okay, and here comes the electronic part that you don't need to bother yourself because we have already taken care of that part. So here's what's happening. So if you're familiar with electronics and the lightings and other stuff, we have LEDs, which are basically small pieces of electronic that provide light. And you have seen them before. Definitely your screen is an LED, but these small LEDs, like they are coming in different sizes. But for us, the LED that we have is like this size, like smaller than the thumbnail. And it has basically a system like this. It has 4 pins. And in each pin, we should tell it what's the red color, what is the green color, and what is the blue color. And it also gets power from this one also. So this is the negative leg. And then if we send values to these RGB pins, it is going to give you different amount of RGB color. And eventually, it's going to give you a combination of these 3 to form a solid color. Okay, so basically it means that if you have an LED, and if you have, for example, an Arduino board, and if you're not familiar with what is an Arduino board, this is an Arduino board. You have an Arduino board actually connected to our robot that reads some data from the robot. And then from the other side, it sends the data to this LED and it generates different colors. So if you have this RGB, this LED, Arduino board somewhere on our robot, so this is the Arduino. From this side, it needs to read something from the robot, for example, some signals, and then it can send some signals to our LED here and gives it some command to get different colors. And eventually this LED is going to show us the colors that we want. Okay, so again, we need to do something on the robotic side. And then the robot should send some signals to that Arduino board. The Arduino board is going to take care of converting that signal into a color that you can see on this LED. So to be honest, we are going to take care of this part for you. So no problem for you on this side. The only thing you need to do is to send some signals from the robot to the Arduino board. And we did the wiring and everything for you. And then eventually, we just want to say, okay, from these colors that this RGB LED can generate, would you please generate these ones like this color and assign it to the first target? And for example, this color and assign it to the last target. What we are going to do in the next step is just to use the digital outputs of our robot to generate a proper color to be used in the Arduino platform. So what we are going to do is to actually find a way to convert these colors that we get here into a bunch of numbers that we can use with the digital outputs. If you want to get a little bit more familiar with what's going on here, here's the process. On our robot, we have defined 8 digital outputs. And however, we are going to use only 5 of them. So they are called digital output 1, digital output 2, and it goes all the way to digital output 7. These are the digital outputs that we designed on the 120 robot, and you can use them anytime that you want. You can use the teaching pendant to set them. You can use your rapid code to set them. Whatever you want to do is possible. And then we have some electronics connected to our controller that actually reads these digital DOs. And then it's called optocoupler, I think is the name. So I say, let's say it's OC, optocoupler. And then it sends the data to this Arduino board. And the Arduino sends the data to that RGB LED, and it actually makes the color. So you don't need to bother yourself with this part of it, because everything on this side we have already done. You just need to define these DOs in a way that defines a gradient of numbers. It might be a little bit confusing. These DOs can only be 0 and 1. So we will have 8 pairs of zeros and ones. And you may ask yourself, like, how come I can make numbers with 0 and 1s? And that's actually not a big deal. we are just using these digital outputs as bits. So basically it means that if you have 8 digital outputs, like this, we can, generally speaking, use them just like bits on our computer, like 0 1s. So you know that, for example, 0 0 0 0 0 0 0 0 is actually equal to 0. And if we make this one like 1 0 0 0 0 0 0 0, it's actually equal to 1. Oh, my pen is not writing down here. So that one is 1. And if you have, for example, 0 0 0 0 0 0 1 0, it's equal to 2. So there is a way to convert these digital outputs into numbers. We just need to find a proper code to convert these digital outputs into numbers and then feed them to the Arduino board that we have. And again, we have already taken care of this one. So if you open your the downloaded file that you had, it's already, let's see, where is it? It's here. So you just need to copy paste this piece of code from here. So if you open it, it's actually a Python code that converts these numbers from your the numbers from your gradients into 0 and 1s. So just copy paste this one. So I'm holding Control C and I get back to my file and I Control V it here. And it jumps somewhere in the corner here. And just to double check, let me see. Okay, it just needs the X value. Okay. So we have a Python code that receives a range of numbers, and then it breaks them down into a binary format. So for example, if we give it 1, it's going to convert in 0, 0, 0, 0, 0. I think in this case, it's only reading 1. So if we give it 2, it's going to convert it into 0, 0, 0, 1, 0. If we give it 3, it's going to be like 1, 1. And I think 2, 4, 8, 16, 32. It can actually make 32 numbers. I think 32 is going to be something like 1, 0, 0, 0, 0. Yep. Am I correct? No, it's going to be this. Actually, it goes all the way to 31, which is this one. Oh, let me just clean it up. It goes all the way to 31. And 31 is this. Correct me if I'm wrong. Okay, so here's the part that actually converts these color gradients into bits that can be sent as the digital output on the robot. Here's the catch. This code only receives numbers between 0 and 1. If I get back to this code that I gave you here, you can actually inspect and see what are the numbers that I fed into this model. Oh, it doesn't. It actually works with any number that we give it. So no problem. Good for us. And it brings back these 0 1s. So no problem, actually. That was my bad. So basically, it reads numbers and it converts them into binary format. So let's see, what do we have here? So our numbers are actually here. So I feed all those numbers to my Python code, and it converts them into a bunch of binary codes. Let's see, what are the binary codes? Oh, good. So we get like 6 digits, not 5 digits, my bad. So it gives us 6 digits. And on each set of digits, we have the color that we want to go for. Okay. So you can see that the first one is 1 1 0 0 0 0 1 1, and then it changes for each color.
My like Python is complaining when I connected to Z, and also said no data was collected.
So okay, let's see. When you connect it to Z here, you should have these numbers. Okay. Does your Z have these numbers? So when
it has a lot of numbers.
Okay, but when you connect it here, and did you connect it to X, not Y?
Yes, it is X.
Okay, and what's the message that it sends you?
It said no data was collected.
So can you share your screen? I think I know what's going on there.
Oh, okay.
That's interesting. Okay. That's quite interesting. Can you click on that red switch and like red panel on the right side of the Python script? Yeah, that red one, that red window. Yeah. So solution. Okay. So. Oh, okay. So I think you have a float number fed into this one. Can you connect that output into that panel? Okay. So let me see. So it's complaining about having the float number being converted. Can you right click on X, like the X that you have here, right click and type hint, go down, it says type hint, and make that one integer.
Oh.
Yeah, that's fine. Now connect A to that panel. Yeah, you have the numbers.
Oh, okay.
Good. So I think when you're copying these components from that part, it doesn't actually correctly bring the formats.
I wasn't able to like copy the component directly, so I just create a new one.
Okay, so if you have created a new one, that's the case. Okay. There might be one difference between the file that I have and the one that you have. I think I should have edited that one. So if you double click on this Python thing, it opens the code for you, and you can actually, I think in your case, this number is 7. So please convert this one into 5. So this number should be 5, not 7. So the point is, when I made that octocoupler, it actually reads 8 numbers. But once we try to use it, we realize that Arduino that we have only receives 6 numbers. 5. That's why you need to convert this number into 5. So if you,
I think it's already 5.
Oh, it's already 5? Because on that file, I thought it's like 7. Okay, good. So we get these numbers, no problem. So we have whatever we want. So let's go and see how we can convert this into a bunch of digital outputs. So let me also check the code, make sure that I'm not making any problem here. Good. Okay. Good. I think we are fine on this one. Okay, so we have these digital output values. So we see that it says 1, 1, 0, 0, 0, 0, and 1, 1. Somehow we need to make digital output control for each target and say, okay, I know that we have like 7 digital outputs in this case. Oh, no, I remember. I kept the first one for turning on. We have this number of digital outputs. And at each target, I want to set digital output, to set these digital outputs to be on and off, in order to prepare those colors for me. So basically, what I'm going to do here is to actually define a bunch of move commands. So at the end, it's going to be, for example, move J. So the robot goes to that target, and then it should actually do a lot of set and reset for DOs. For example, DO1, DO2, set, reset, set, something. So we need to go to, for each target, we need to go to that target, for example, this target. And once the robot arrives on that target, we want to set all the DOs in the correct way to generate that color. Okay? So we need to, in our toolpath, generate the data set to do this for us. So basically, what we are going to do at this moment is to generate a bunch of these set, reset things to correspond with this data set that we have here. Okay? So for example, for the first target, we should say that please grab the DO1 and set it to 1, grab the DO2, set it to 1, grab the DO3, reset it to 0, DO4, reset to 0, DO5, reset to 0, DO6, set to 1, and DO7, set to 1. And it's a cumbersome task to do manually, so we are using the magic of Grasshopper to take care of us. So what I'm going to do, I'm going to use that setDO command. And where is that set reset DO? I think I have so many components on my Grasshopper that it's really hard to find them, so I need to manually find it here. So digital output, where is that? Oh, somebody help me finding it. It might be here. Okay, with the value of digital output, change the value of an online digital output. Okay, it's here. Let's see, it's the digital output. I think
this one is different from the one.
Yeah, I think I have a different one here because, yeah, it's this one. So it's set reset DO. Okay, so let's see if I can find. Oh, it's here. Okay, good. Thank you for reminding me on that side. Okay, so for example, this component just reads the signal and the name of the digital output that we want to change. And it automatically says if the value is 0, it's going to reset it. If the value is 1, it's going to reset it. Yeah, set it. Okay. So let's do it. Like I'm going to first test it. So imagine that we have DO01 and we want to turn it on or off. Let's see. So at the beginning, it doesn't have any information. It needs to know exactly what we want to do. So I'm going to just use a button here to give it some Boolean value. So you see that when the value for this one is false, it actually resets digital output to 1. And reset means that it sets it equal to 0. If you push this switch, which results in true going through this component, it's going to set that component. So maybe it's better to have a look here and see what's going on. Okay. So you remember this switch from exporting our code. So whenever it's false, it makes a reset. Whenever it's true, it's make a set. Okay, set, reset, set, reset. That's going to do the job for only one of our components. Actually, maybe we should go for this one also. So this is the funny thing about Grasshopper. It also reads number as true and false. So if it's 0, it's going to be reset. If I set it to 1, it's going to make set. Okay, because we are going to use this one for now. Let's just use this one. Okay, but we know that we have like 7 of those digital outputs, and we want to repeat it for like, I don't know, 60 targets that we have here, or 50 targets. We need to find a way to generate 360 of these digital outputs. So what I'm going to do here is to actually convert this component into a little bit longer piece of data. So if I make this panel here, and right click on it and says it and convert it into multi-line data, you will see that by the number of digital outputs that I provide here, this component is going to generate the same number of outputs for me. So I know that in that robot, I have 7 of these. So 5, 6, 7. And I can go for like 3, 4, 5, 6, and 7. And you can see that because I have 7 elements on this side of this panel, it also generates 7 set DO for me. Okay, so here we are using something that's called data structure and data tree structure in Grasshopper. On this side, I have 7 inputs. On this side, I have only 1 input. Grasshopper combines these 2 and generates 7 outputs for me. Okay, so for each target, I get these 7s. The question is, okay, I have more than one target. I actually have something like, I don't know, 50 targets. Can I provide this system with like 50 pieces of data and get the outputs? And not only 50 pieces of data, but 50 pieces of points. And in each one, I will have like 7 pieces of information. Can this component actually generate those for me? I would say yes, but let's go slow and one by one. So we have this digital output 1, 2, 3, all the way to 7, and I want to set different values for each of them. So let's say that we want to replicate whatever we have in this first branch of data here. So imagine that if you want to generate the data that we have here, we want to see if we can match these digital outputs with the values that we have over there. So let's say that the first one is 1, second one is 1, third, fourth, fifth, 6, and 7. So we have 7 pieces of data. I convert them into multi-line data.
Sorry,
And you can go ahead.
Do we have to follow you on this part?
For now, you can just listen and like to see what's going on here. But then I'll tell you when to follow. So here you see that it actually matches the first set DO. The first DO is matching the first one here. That's why we have set. Okay, but for example, if you go for number 2, index 2, which is the third one, you see that this is DO3, and here it says, oh, okay, sorry. Here, this one. It's 0, so this one becomes reset. So basically, Grasshopper at this moment matches the data that I have and says, okay, you gave me DO, this DO. You gave me this DO, and you told me it should be set to 1, so I'm just taking care of it. You have another one here, that's DO4, and you told me it should be set to 0, so I used reset. So it's basically matching these data together and does the job for us. And if you're familiar with Grasshopper, this is like the classic Grasshopper matching 2 lists together as long as their paths are actually the same. And what do I mean by path? I mean like here and here. There are a couple of things that are matching. First, these paths are matching. They are all 0, 1 branch, and they also have the same number of data. All of them have 7 pieces of data. It works. But there is something a little bit more interesting here. Here, our data structure is slightly different. We have 3 branches of data, and inside each branch, we have 7 pieces of data. So if you're not familiar with the Grasshopper data structure, it's basically like this. Grasshopper makes a tree of data and calls the branch of tree as 0. Okay? And then it makes some, like the trunk of the tree is 0. Then it makes some branches of that tree and call these things like branch 1, branch 0, branch 1, and branch 2. And then inside of this branch, you can have like sub branch like this one or something. And then your information, these values are just like a fruits on this branch, like 1, 1, 0, 0, 1, or whatever. So this is a data structure of Grasshopper. And whenever you are trying to do some operations over 2 or 3 pieces of data, Grasshopper tries to match their data structure and does the job with the same objects that are in the same address. So we will get a little bit more complex in this side, but you should definitely have a look and search for Grasshopper data structure and get more familiar with it. So right now we have, okay, let me just unravel this one so you can see what's going on here. So here we have 7 digital outputs, and we have a bunch of targets that want to have those digital output sets. So it's the fun part that the fact that Grasshopper actually takes care of this one for us. And just by connecting this Python output to these 0 and 1s, and then fit it with these DOs that you want to work with, it automatically applies all those set and resets for you with no problem. You see that? It generates everything for you. And that's the beauty of Grasshopper. And we should appreciate it, because later on it gets really dirty and really confusing. And you will appreciate the simplicity of this specific assignment and workflow. Okay, so this way we have the set and resets that we want to use in order to make our motion commands associated with the digital outputs. And that's actually pretty convenient, because we just grab these commands and connect it to commands here, and that's it. That's it. Actually, if we go here and convert this one into code generation, you will see that after each robotic motion, oh, I need to still add one thing. So basically, my bad. I just jumped into conclusion and I forgot I need to add something else. So basically, right now in our toolpath, we have these commands, like you see these all these set DOs and set reset DOs. We have them combined together, and this toolpath creator somehow embedded these commands to our workflow. But if you look carefully, it is not embedded in our code. So if you can see that the motions are here, motions are here, and those digital outputs are also here. And they are not intertwined. So basically right now we have these, it's funny that you can, oh, your screen is like way behind me in this process. So basically here, we have a bunch of digital outputs. You see these digital outputs, or something is wrong with this screen? Okay, now we can see it. I think there's a lag between the time I'm speaking and the time it's actually showing up on my iPad. So it's getting a little bit confusing. So on the left side, you see that all these digital outputs organized in branches of data separated from each other. And if you scroll down all over them, you will see that we have all the way to index number 39, which means that there are 40 of them. And then we also have 40 move commands. Somehow we need to grab these move commands and connect them to these motion commands. And to do so, we need to somehow match every single motion command that we have on the right side to match the data structure of the data on the left side, which is a little bit scary for now. But let's see how we can do that. So right now, go ahead.
Into that, I just need to double check to see where you put your command output into.
Okay, so the commands are actually first connected to the commands in your toolpath. Maybe a better way to do this is to actually use this trick. Okay, keep everything here. And then zoom for a second so everybody can see what's going on here. So basically what I've done is connecting these commands to the commands input of the toolpath creator. And then I can actually make a group here. Now I just want to see like what's going on and if it's make any sense. Okay, now I come back here. Go ahead, go ahead.
Why? So do we need to manually type like DO1 to DO7?
Yes, yes, that's something that we should do manually. There are some, crazy methods to do this. So basically, you can do something like this: DO0, and then series, and concatenate, and you can actually do this. Say start from 1 and 7 of them. Hello. Actually, count is 7. This is 1. Yeah, you can do this also, but to be honest, it's not the most elegant way to write them down, like hard code them, and do the magic numbers. But sometimes if we know that this is going to be always the case, we don't go for this like crazy methods. So let's stay with this one.
Also, like for the like motion panel and also the commands panel, my motion only has one move out, and for the commands, there was no data collected.
Okay, so can you make a guess why you only have one motion? Like maybe your answer is here.
Right now I have. Oh, I see. Okay.
Yeah. You should always make sure that you're on the code generation mode.
Oh, okay.
Yes. Okay. And I realize that there's a good lag between the time I say something and the time it actually shows up on my iPad, so I can draw something for you. So I safely assume that you also have the same lag. So bear with me on this side. Okay, so let's see what do we have here. We have these DOs, which are somehow in a really complex data structure that says 0, 0, 0, 0, and then another one 0, 0, 0, 1. And then we have all these move commands that are in one branch of data. In order to combine these things together and put these move commands at the beginning of each of these set DOs, we need to somehow match the data structure. So what I need to do eventually is to have one move command, okay? And right below it, I should have this set, reset, set, reset, or whatever, okay? I want to have one of these, and then in the next branch, I want to have another move L, another set of set, reset, blah, 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 another structure, and go all the way to the end. So somehow I need to get the data structure of this one, make it simplified, and then convert this side of the motion commands and put them in the same structure that we have on the left side. Okay, so I'm going to do this. First, I need to somehow simplify whatever I get from these commands. Actually, there's a command called simplify. If you hit that one, did you see what happened? These numbers were like something like this, 0, 0, 0, 0. Okay, and to be honest, if you look carefully, the only number that changes in all these data paths is only the last number. So basically, Grasshopper unnecessarily makes this in data structure really complex. And just by using this simplify method, we can get rid of those extra complexity. So basically, right now, our data structure is something like this: a tree with a lot of branches, but in each branch, we have like 7 pieces of data. Okay? But here, in this side, on the motion commands, we have one big list of data with 40 motion commands inside of it. Somehow, we want to grab this data set, data list, or whatever it is, and convert it into something like this: a tree with 40 branches, but in every branch, we only want to have one motion command. To do so, we use this command called graph. So graph means that if you have a piece of data, a list of data, it will grab each item of that data, a data list, and put it in a separate branch. So as soon as I hit graph, you can see that in this data set on the right, I will get something very similar to what we had on the left. So basically, every move command is right now in one branch. So this is the previous condition. All the data in one list, all 40 of them are in one list. When I graphed it, it actually converts everything into a super branch structure system. So you see that it has 40 branches of data. And in each branch, we only have one element. But if you look carefully, here we have 0, 1, 2, 3, 4. But on this side, we have 0, 24, 0, 25. And if we look carefully, you see that only the number on the right is changing. So it's the same scenario as the one we had on the left side. So I can, again, apply this simplification here. And now you see that we have 0. On this side, we have 0. We have 1. We have 1. We have 2. We have 2. Now, if we apply some sort of like merging operation, this first move command actually joins this list of motion, this list of digital outputs. This move command joins this one, and this one joins the second branch of data, and they are going to combine together in a really, really nice way. And that's exactly what we are looking for. After applying graph and simplification, these two data sets have the same data structure, same number of branches, same addresses, and now if we merge them together, they are going to do the job for us. So I'm going to use this merge component, okay? And I will connect the move command, like the motions first, and these digital output commands here. And then if I connect the panel here, you will see that for each branch of data, we have one move L, and this one move L to TP target point 0, and then these 7 digital outputs. Then I will go to move L number one or index 1 actually, and then I have these 7 digital outputs. So this way we managed to get 2 different lists with complex data structure and combine them together. Does that make sense?
I have no question on that part, but like just before, like when I switched from 2 pass preview to code generation, my IKSolver starts to complain.
Okay, can I have a look at that one?
Yes. Okay.
Let's see, what do you have? Okay, wow. Can you make a guess what's wrong here?
I have no idea.
So zoom in on the IKSolver, and then that small window. Yeah, so this, okay, ask that one. The first one says that the robot is near singularity, which means that joint number 4, 5, 6 are getting close to the same line. So if you remember, like if the robot makes this, these 3 are going to be in the same direction, and the robot is going to have singularity issues. And I think on those other targets, the robot tries to reach those targets really hard, so it needs to constantly rotate between like 2 targets with 180-degree rotation. And I think the main reason for that one is the fact that those targets are far away from the reachability of the robot. Okay, so maybe you can make like, can you just move, can you just get into toolpath preview instead of code generation so I can see what's going on? Yeah.
Oh, which one?
The T one. So you can actually see the whole path. Okay. So I think those targets are in really bad position for the robot. So I think if you move everything up, it's going to be easier for the robot to reach out to them. Okay, now go for code generation.
Oh, okay.
No problem. So you always remember, these robots have limitations on their work span and the area that they can reach out to. Specifically for this 1 to 120 robot, like the same level as the flat surface that this robot is installed on is actually not the easiest part to reach out to. So this robot can actually, it's a little bit challenging for the robot to get into its base, like the ground 0, 0, 0. This is the way that these robots are designed. Actually, it's really easy for the like 4400 or 6640. They can actually reach out to the ground almost. This robot has a little bit challenge in reaching out to the ground because in most cases, these robots do not reach to the ground. There's a table in front of them. It's kind of like object holder or something. So whenever you see that there is this singularity issues or like reachability issues, try to move your targets and somehow it may actually solve your problem. Then you can get into more serious solutions like reconfiguration and other stuff. But for now, I was pretty sure because you could see that the problem was raising at certain level. Like below that point, I think below target 179, everything was fishy, like the robot couldn't reach out to them. And you can easily say that this is a problem with the reachability or reconfiguration. So you just move your targets up, problem solved. Okay, so we are fine on this side. Thanks for sharing. Let's get back to this work. Okay, so we have these data structures. We combine them together. We use this magical merge component, and it merged them together for us. Everything seems fine. If you remember from the last time, I asked you sometimes to actually enable this condensed code. So basically, your targets are going to be embedded into your motion commands. So we have that here, no problem. So we have this move L to a specific target with accurate and drawing speed. Oh, there are two typos here. There are a couple of things that I want to edit. First of all, I want to edit this drawing speed and correct the error that I have here. And I also want to make sure they are all move J. So motion value list should be set into combo. So it's actually going to make move J, because we know that move J is an easier way to handle everything. So this is what we need. So basically, we got these colors out of the motion command, and everything seems fine. Any question? Because after this, we are going. Oh, actually, we need to combine them. Sorry. So we have all these like motion commands. Now we need to feed these into our operations. But here's the catch. If we do so, there would be this little problem. Our code is going to be generated for 40 times. So basically, if you look carefully at this piece of data, HAL is generating one rapid module here for one move, then makes another one for the other move, and then it generally makes like 40 of them. The solution for this one is to eventually flatten our data and kill the data structure. So rapid is going to put everything in one procedure. So we did simplification on our motion and on commands to simplify the data structure. We applied graph to break down our motion commands into 40 branches of data so it could match our commands from here. And then we merged them together, so they actually connected to each other in the correct order. And then we flattened them in order to have them in one piece. So this is a really complex procedure. I'm not expecting you to completely master it at just one run. You should definitely try this data structure more and more and more. Just Google Grasshopper data structure and data tree, and definitely do some research on that side and do some exercises on that side. Because during this semester, like during the rest of the semester, we are going to do this a lot. And if you lag behind in this side, it's going to be a serious problem. I guarantee that if you do not understand exactly what's happening with these data structures, you are going to waste hours and hours and hours when you are doing your assignments. Trust me, this is confusing if you don't spend enough time on it. If you spend like 2 hours this weekend, do some research on Grasshopper data structure, then you will save at least 10 hours later on down the road. And if you're doing anything else with Grasshopper anywhere else in any other class, you're going to be way more comfortable doing it. So this is the easy part for today. Just assigning the colors and letting that Arduino thing taking care of the colors for you. But as you remember, it wasn't our final solution. If you remember, you're not supposed to just make one curve. We were supposed to make more than one curve. So this is the easy way of doing it. What if we have more than one curve? What will happen if instead of having one path, we have multiple passes? So for example, instead of having this, what if we have, for example, two curves? So in order to make everything harder for everyone, I'm going to add another curve here. Let's say we are going to edit that curve. Maybe I should make a little bit more complex curve, like this one. And this one. Oh, that's too far. move vertical. Yeah, that's something meaningfully manageable. So what if you have two curves, one like that ellipse and one like this one? And what will happen if we try to have both of them functional? And that's going to be a little bit mind-blowing. Okay, so my suggestion is to actually save this file and keep it somewhere safe, because this is the bare bones structure that we are going to use. Then let's start working with multiple lines. The final goal was to actually use that crazy curves that I had on the other layer, but let's start with something simple like these two curves. And to be honest, even easier than this, let's do something very simpler than this one. Let's move this curve here and make it two curves and just move it around. Okay, so I'm going to move this curve for a little bit. For example, in the X direction. And I'm going to move it for like 100 millimeters. Maybe it's too far. Let's put it here. So I just copy pasted this path, this curve for a little bit, so I can actually work with two curves rather than just one curve. As I mentioned, please save your file and make sure that everything is working, and then work with the new version of this file. So I'm going to save this document as like multi-line, and I start working on this one because I don't want to destroy whatever you had so far. And my suggestion is also to disconnect this command here. Okay, we are going to disconnect this command, so whatever we are doing, it's not going to affect the rest of our code, because it may take a while for this computer to actually process everything. So let's see what we can do with two curves. We have one curve here, and we have one original curve. Let's merge them together so we'll have two curves in one path. Good for us. So right now we have two curves. Now we can divide these two together. Okay. Now we have two curves, and they are connected to this divided thing. So we have like 80 targets. And if I check the data structure here, so you can use this component, parameter viewer, to see how many targets do you have. So for example, here you can see that I have one branch of data, and in one branch of data, I have two pieces of data, which means two curves. So I'll check it here, make sure that it's exactly what I'm thinking. Yes. So one branch of data, so you don't see these like dark headers, only there's one of them. So it says there's a curve and there's another reference curve. Basically means that a copy of the same curve. And we see the same thing. But let's see, what do we have in our points? So we have a bunch of points here. And then somewhere at the middle, the data actually branches out, and it gives us another bunch of points. So here we have two branches of data. So if you remember those data trees in Grasshopper, we have two of them. In each, we have 40 targets. Is that clear? Like what's going on here? Instead of having just one branch of data, we have actually two of them. And if you use the same parameter viewer and double click on it, it's showing you this. So it says that there are two branches of data, and inside those branches, there are like 40 pieces of information. That's something like pretty trivial regarding the Grasshopper data structure.
How do we like switch to the tree mode?
Just double click on it. You see
Oh.
that? I'm just double clicking and it's showing us
Okay.
everything. Okay, so two branches of data. In each, we have 40 targets. Okay. One bad piece of advice is to use the same data structure that you made, or the same components that you used for one piece of data, use it for the rest of it. Like, it's actually not a good idea. Whenever you are working with something that totally works with one piece of data, like one branch of data, it's going to mess up everything if you use it with more than one branch. So my suggestion is to actually start working again from scratch. So we are not going to use this thing that we made previously. So let me just put it somewhere else. So again, as a basic advice, if you make something for only one branch of data, and then say that, yeah, later on, I'm going to make it for like multiple branches of data, this is going to result in a disaster, okay? So if you want to make something for multiple branches of data, like the one that you see here, start from scratch. Most of the time, it's not gonna work. You are going to mess with something somewhere down the road, and you make some data mismatch, and your computer is going to freeze, and then everything is going to go downhill, and it's not a good practice. So I'm going to start from scratch. If you remember, we had a bunch of points. So I'm going to make a new point component and grab everything from here. Or if you're more comfortable, you can grab the data from here. And you can see that this is actually a dotted line. It means that we have data structure. If you look here, you see that it's a solid line because there's only one piece of information in it. And I think if I graphed it, it doesn't make any difference because it's still one piece of information. But if you have multiple pieces of data in the data structure, it's going to show you this. If you have only one branch of data with multiple items in it, it's going to show this like double line. So if you look carefully, you see that there are two pieces of information with one branch of data, it's double line. If you have one piece of information in one branch, it's going to be a solid line. And if you have multiple pieces of data in multiple branches, that's what you will get. So this is also a visual inspection. So, okay, we have all these targets. We want to do that color things that we discussed earlier. So if you remember, if I add the gradient again, the gradient is asking for L0 and L1. Previously, what we did was pretty simple. We said that, okay, give me the bounds of this, the bounds of these colors, and break it down into deconstruct a domain, and it would give you the beginning and the last of all those targets. And what we were doing was actually, X, Y, Z, we need to deconstruct that point and use the Z value, to be honest, not this one. Okay, and we could actually fit this Z here and everything would be fine. We could use that custom preview. And these are the geometries and these are the colors. Everything seems fine, am I right? Like everything is fine, the colors are correct, but there's a small catch here. Let me just make everything a little bit crazier by adding a Z value instead of X. So instead of X, let's use Z. And actually add vectors. Okay, good. So instead of just moving that curve in X direction, I moved it in X and Z. So they are like diagonally on top of each other. If we do this, then there would be this really, really small trick that you see. So I just move this other curve, not only in X direction, but also in Z direction. And now if you look carefully, you will see that instead of having the purple light color here and the red ones up here, it actually breaks down the data in two pieces and says, okay, I'm going to apply the purple color for the lowest part of this curve and the red color for the toppest part of this curve. And I'm going to apply the same thing for this one. So Grasshopper treated everything as separate. Let me just change these colors into something more tangible here. You see that? It treats these curves on the left totally different from the things on the right. But to be honest, I wanted to have a green light here and red here, and everything in between should be the gradient. So I should still have some yellow here rather than red. This one should be also yellow, and this one should be red. The reason that we get these like two separate entities is the fact that we have two branches of data And those two branches of data providing me with two piece of minimum and maximum and everything. So basically here, if I put that data structure viewer, you will see that I have two branches of data, and Grasshopper calculates the boundaries for each of them separately, and then make these like start and end for them separately, and it will result in a bunch of colors that are separated in two branches. I actually want to make sure that I know the exact lowest value, the lowest Z value for all these points together, and then the highest Z value for the whole points together. To do so, I'm using another trick that's called flatten. So look what's happening here. If I right click here and I use flatten, Grasshopper immediately assumes that I want to treat the whole data as one branch. So to make everything a little bit clear, there's a component for this one. So I would say I want to flatten my data set, and let's see what will happen. So this is the original data set, 2 branches with 40 elements in each branch. When I'm using flatten, it flattens the whole data structure and breaks it down into one list, and all 80 elements are going to be in the same list. Imagine like we have 2 classes of 40 students, and then it says like break time, all the students from their classes go to the backyard, and then like you have, instead of having 2 groups of 40 people, you have 80 people in one group. So that's the way the flatten works. If you have a data structure, flatten breaks it down. It keeps the order. It still keeps the order. So the first element in the first list is going to be the first element here, and the last element in this list is going to be the last element. So 40 of them from the first list is going to stand in front of the other 40 from the other list, and this order is kept. But doing this trick result in this. We will have only one boundary, and we will only have one lowest value and one highest value. And this is going to give us this spectrum a better understanding. However, we still keep our data structure when we feed the T value. So let's have a look what's going on here. So we have only 99 as the lowest value. We have 232 as the highest value, but we want to get the colors for each of those points separately. So we feed the Z with its data structure. Okay, when we do so, it generates the same data structure for us. So we have 40 points in the first list, 40 points in the second list. That's because our T value was from this structure. Okay, so this is really interesting. You can actually mix and match different data structures together to get the results that you're looking for. Okay, so we get this 40 colors in 2 branches each. So in total, we have 80 pieces of data. You remember I mentioned it's not a good idea to grab whatever you had previously and just change it, because the reason is that it's going to confuse you when you are trying to apply these graphs and flattens and other stuff. My suggestion is to actually make everything from scratch until you get really, really comfortable with everything. To be honest, it's like 99% similar to the one that we, not 95, 90% similar to what we've done before. The only part that's changed right now is this flatten. But in order to understand what's going on in this flatten, we need to actually make everything from scratch. Is that clear what's happening here?
Yes, but after I flatten my data, it still follow the color is still following the old way. Yeah, I don't know why.
What's happening?
When I flatten the data, yeah, the color should be like a continual things, like from yellow to yellow. Yeah, but for mine, it's still following the old way. Yeah.
So are you sure that you have collected everything? Like, oh, do you see that I flattened here, not here?
Yeah.
So you have
I
you still have
flattened at the B and D.
Do you want to share your screen so I can see what's going on?
Yeah. I think this would be best.
Let's see.
Yeah. Can you like see my screen like here?
Yes. Because you have the same, like because the Z value for both of your spirals are actually the same. That's why you have the situation. That's why I actually moved one of the spirals a little bit higher. So instead of using that, so do you see that you're moving it along x-axis? So try to move it also in z-axis.
Okay.
So no, you can still keep that move. That's fine. Just add a z vector here. Okay.
Add to here?
No, you need to add them together. So put an add component, like add. Yes. Addition. Okay. So add x and y, x and z actually. Yeah. And then connect it to T.
Then move it to T.
I think right now your z value is really small. So that slider that you use for x, you can also connect it to y, to z.
Yeah, that works.
Now you see. Okay, good.
Okay.
Yes, so it seems that it's working.
Yeah, okay, thanks.
Okay, so let's get back to my screen. Oh, I have some electronics here. Okay, so we have these pieces of information that can actually help us with the workflow. That's good. Now what we are going to do is a little bit scarier. Now we get all this information. We need to grab that Python code with this part and this part and see if they are going to work. So the Python code, the digital outputs, and the values that we were looking for. So let's connect this one to X of the Python code, and then it's going to give us, no, I actually need to get these, and where was that? Why am I getting confused? Okay, the Z value. Okay, so we need to connect the Z values, and let's see what will happen at the end here. What type of data structure we get. Oh, it's actually doing the job for us. So it's not only working on one branch of data, you will see that it adds one extra branch. So it's 0001, 001, 002, 3, 4, all the way. And then somewhere at the middle, it actually says 010, 012, and it goes all the way to the end. So this data structure is pretty similar to the targets that we have here. And it seems like what we are looking for. I just need to simplify it to make sure that we don't have any of those extra zeros. So the first number, the first 0 means which curve are we in. Okay, so we have 2 of them, 0 and 1. And then the second number defines which point we are actually defining these digital outputs for. So this is a good one. So let's go ahead and feed it into our motions. Actually to commands. And we immediately get some like angry message from our toolpath preview that says the tree of additional command is not equivalent to the list of targets. We need to double check and see what is our data structure on the targets. So I'm going to check the data structure for the targets, which are here. And as you can see here we have 2 branches of data, each with 40 elements. So compare it with this. Here we have 80 branches of data. Here we have 2 branches of data. So can you guess how we can convert these 2 branches with 40 elements each into 80 branches of data? Can anybody make a wild guess? So basically what we are doing is this. Go ahead.
Well, I think like maybe merge them together or whatever. I don't know.
But yeah, we need to eventually merge them. No problem on that side. But we should somehow convert this data structure that has 2 branches with 40 elements inside to become a data structure with 80 branches. So go ahead.
Yeah, graph.
Yes, graph is the king here. So if we graphed everything, you will see that we have 80 branches of data that's matching this, but there's one catch. Here we have 000, here we have 00. So it seems that if we just use simplification, these two branches of data are going to match. So 0, 0, 0, 0. If you go all the way to the end, the last one is 139, 139. Now we can actually use these two to work together. So I use this one as my target and still gives me some angry messages. There might be something wrong here that I'm not aware of. Okay. So let me see what's the data structure here. Yeah, data structure is exactly the same. Why we still get that error? The tree of additional command is not equal to list of tree. It has been ignored. Okay, it says something is fishy, but I do not trust it because we have 80 branches of data and we have 80 branches of data, so they are actually the same. Okay, I'm going to ignore it for now. Let's see if it's going to get back to me in a bad way. This is a flip override, doesn't match the target. Okay. Yeah, I don't have flips, so hopefully it's going to work pretty fine. Okay, so we have these pieces of data. Everything seems like magically working, no problem. Let's have a look here and see what will happen in that area we were trying to match all of our information together. So here, let's see what we have. We have this data structure with 80 branches in it. Here again, we have 80 pieces of information. Oh, that one is empty. I think somehow Grasshopper messed with everything and tried to mess with us in the same way. So what I'm going to do here is to actually just grab it from here, combine them together, and yes. So let's see what do we have here. So we have 80 branches of data. And here we have 80 branches of data, but in slightly different structure. Okay, got it. I think we have this error here. Yes, got it. So we just need to flatten this part. My bad, because yeah, that's why I am telling you, you should not just simply assume that it's going to work in an easy way. Okay, so that one works. That one also may work. Okay, so what do we have here? We have the motions, we have one toolpath. Let's see what do we have here. I'm going to remove this simplification. I'm going to remove this graph, and I'm also going to move this simplification. Okay, so commands, we have, okay, all these pieces of information, that's fine. And in motions, we have all these 80 commands. Now we should find a way to combine them all together. Whew, that's going to be the challenging part. Okay, so go ahead.
Graph, we like replace it with simplify.
Where was that?
Which part? Change you just made.
Oh, okay, so basically, this is the problem, not problem, but one of the challenges of working with this toolpath creator. Toolpath creator is not working just basically based on the, like, if you provide it with 2 branches of data, a toolpath creator is going to make 2 toolpaths for you. Okay, that's the challenge here. So if you look carefully here, I have 2 branches of data. If I directly feed this one into my toolpath creator, you will see that it's making 2 toolpaths for me, okay? Which is not what we are looking for, okay? So I will flatten this in order to make only 1 toolpath, because like 2 toolpaths is not what we are looking for in this case. And actually we can do that, like we can actually, we can combine these 2 toolpaths together and then use the weld toolpath method and get 1 toolpath together. But it's to be flattened, and then we get 1 toolpath. But it's not exactly what we are looking for. So I'm just flattening these 2 curves and make sure that we get only 1 toolpath. And then I'll try to merge these things together to find the solution. So Here in the post processor, we need to check our data and see what exactly do we have. So we have these motions here, which are 80 motions. And then we have all these commands that are basically 80 branches of data. Okay, seems a little bit scary because if you look carefully, even if we use the simplify command, these data branches are all the way one after each other. So there are 80 branches of data. In each, we have 8 pieces. And there is no easy way to break it down into like 80 pieces of information easily. So there are 2 ways of doing it. I think one way to do so is to actually break down this toolpath into 80 branches and try to match this, or somehow break down the structure of these ones from these like 0001 and all the way to 180, 140 into 1 all the way to 80. So I'm going to go with the second pass. So instead of having this like 00, like you see that it starts from 00 and goes to all the way to 10 and then all the way to 139. I'm going to convert this one all the way from 0 to 80. And that's something that's easy to do, not that hard. So basically what I'm going to do is to flatten this tree. Okay, once you flatten, it's going to be this, 624. And then I'm going to use a command that's called partition list. And partition list is going to break down a data structure into pieces with the same length. And I know that each piece should be 6 elements. So because I know that for those, it was 6 or 7. Yeah, I think it's 7. Yeah. So for 7 elements, just 7, am I right? Let me just double check. Yeah, actually 8. Okay, so if I do this, you will see that I get this data structure that's like this. Why is it getting 78 rather than having like all the 80s? I think I made some mistake somewhere in the road, but yeah, it should be the same. I don't know why it's happening. So I'm going to simplify this one. So the data structure should be like this. And right now, if I graph the other one, so we have 80 branches, and if I don't need to actually simplify it. Yeah. Now these 2 data structures are matching. I can merge them. And if I merge them together, we will get that data that we need. You see that? Move J, reset everything all the way down. And if I flatten this part, it is going to be what we are looking for. So operations here, problem solved. Okay, so this is the part that's getting a little bit scary and confusing, but basically that's it. I flattened all the commands, and you see that all of them should be 8 pieces. I don't know why something is fishy there. And then I made it flatten, so 624 elements. And I broke it down into smaller lists, each of the size 6. And it gave me this data structure that actually matches the motion commands. I merged them together, flattened them together, and then I generate my code. So this is it for today. I will double check and see what was that error with the last couple of digital outputs. But basically, this is what we were looking for and what we got. I think we're running out of time for today. Is there any question?
How do you know like this number 6?
You mean number 8, am I right?
Yeah.
Because 8 is coming from here. It actually should be 7. I don't know why is it getting 8. Yes, that's one of the questions that the 8 is coming from here, I guess. Yes, 8 is coming from here. We should have actually 7 here. I'm not sure. I need to double check this piece of code. Yeah, I need to double check this part. I think the number problem was coming from this part. I need to check that one later on. No, that's not the case. I need to check this one. I'll check this one. I will get back to you in an announcement later today to figure out what was wrong here. But that number, that should be actually 6. I don't know why is it getting 8. But the point is, this is going to break down your list of any element that you have into smaller lists with the same length. It's really helpful when we know that our codes are actually exactly the same length. There's more complex ways to do it when we are not sure about the the length of the list. I'll double check this one and see what is the problem with that number, and I will get back to you. Okay, any other question? No? Good. So that's it for today. Definitely this weekend, have a look at data structures in Grasshopper. Get familiar with these flat, graph, merge, and other stuff. There's one more that I didn't discuss today. It's called Weave, which is also really helpful later on when you're doing something. Have a look at these things in Grasshopper. It's going to help you in so many different ways that you're going to enjoy playing with it. Okay, so that's it for today. Go ahead.
Sorry, there is something wrong about my IKSolver. It warns the list of flip overrides does not match the list of targets. It said that all flips are canceled.
Yeah, the reason is that the data structure here may not actually match. Maybe you didn't do this like flatten here. That might be the case.
Yeah, but actually flat in the XY plane. Mm-hmm. Yeah, I flattened in the component. I didn't yeah, but I flattened it.
Okay, so, can you share your screen briefly?
Okay. As you can see, here I flatten.
Mm-hmm. And then you graphed it, and then you connect it to the Grasshopper. Do you see that? Yeah. You have a graph, like the one connected to target?
Uh-huh.
That's the graphed one. You need to connect the flattened one.
Oh, you mean this one?
Yes.
Oh, yeah. Oh, they're all fine. Yeah, okay. Thanks.
Great.
Thanks.
So see you on Tuesday. And keep an eye on your announcement because I'm going to find out what was wrong with that element. Okay, sorry, I have a meeting that's already started. So should be a message or on a Slack or anything to just double check if you have any questions or problem. Thank you.
Okay, thanks.
Take care.
Bye.